Right, so in this lecture, I'm going to be talking about another approach for name entity recognition, and we use the few-shot learning. We leverage few-shot learning for better NER. So I'm going to be explaining this paper in 2021, and we are leveraging this paper in 2017, transforming Wikipedia into a large-scale fine-grained entity type corpus. And we are also leveraging this paper for noisy student improves ImageNet classification. So this paper presents an empirical study to efficiently build name entity recognition systems when a small amount of in-domain labeled data is available. Based upon recent transformer-based self-supervised pre-trained language models, we investigate three orthogonal schemes to improve model generalization ability in few-shot setting. The first one is meta-learning to construct prototypes for different entity types, and task-specific supervised pre-training on noisy web data to extract entity-related representations. And the third one is self-training to leverage unlabeled in-domain data. So different concern, and we combine all of them. First, a quick background on few-shot NER. I have a playlist for few-shot learning, but here we are using it for name entity recognition. In the classical way that we have a sequence of tokens, we have T tokens, and we have a T labels as well. For example, each one could be any name entity. So the training data set, N is usually small. So traditional NER systems are trained in the standard supervised learning paradigms, which usually requires a large number. So usually N is very, very big. But in some cases, N is very small. For example, in biomedical literature, you don't have you have many entities, and you don't have a lot of labeled data for everything. So that's why you can also use few-shot NER. So following this self-supervised pre-trained language models, a typical method for NER is to utilize a transformer-based backbone to extract the contextualized representation. And then we use a linear classifier followed by a softmax to project the representation Z into a labeled space. So this is a labeled space. So end-to-end learning objective for linear-based NER can be obtained via a function composition with trainable parameters. And the pipeline is shown in figure 2. The model is optimized by just minimizing this cross entropy. So this is scale divergence between two distributions. And the prediction probability, this QY given X, is just the softmax of WFX plus B. And so in practice, theta 1 is always updated and theta 0 is frozen. So when only a small number of labeled tokens are available, it renders difficulties for the classical supervised training, fine training approach. The model tends to overfit the training examples and shows poor generalization performance on the testing set. So we provide a comprehensive study specifically for limited NER and explore three orthogonal directions as you see. For the first one, how to adapt to meta-learning such as prototype learning, proto-based methods. Also, how to leverage freely available web data's noisy, supervised pre-training data, because we have very freely available pre-trained data. And the third one is how to leverage unlabeled in-domain sentences in a self-supervised manner. So we are using this prototype method. Also, we are using self-training because we can have a teacher and a student model, and with this video distillation. And the third one is the noisy supervised method, because we have lots of data from Wikipedia, we can leverage them. For example, for prototype-based methods, it is natural to adapt this idea to few-shot NER. The core idea is to use episodic classification paradigm to simulate few-shot setting during model training. Specifically, in each episode, M entity types are randomly sampled, and we have a support set and a query set. For example, Gates founded Microsoft. We get distance to each of these, let's say, each of these centers, and we can see which of them belongs to which category. So the rest of that is just the classical protonet, because you average all of the representation and you see to which of these is closest, which of these proto, because we have many, for example, we have 3 classes and each one has proto representation, and we want to know, for example, if you are here, for example, this one is closest to this proto, which is number 1, for example. And so this distance, we understand that among 3 different classes, which one is closest one. So we can categorize and classify any new test data. So we are just, as you see, it's just nearest neighbor for the inference. And for noisy supervised training, pre-trained language models treat each token equally, which is not aligned with the goal of NER, identifying name entities as emphasized tokens and assigning labels to them. For example, this one, PLM treats 2 and Congress equally. So Congress and 2 are treated equally. But NER aims to highlight entities like Congress and downplay non-entity words like 2. So this intuition inspires us to endow the backbone network with an ability to upgrade the representations of entities for NER. So the algorithm, first we learn teacher model via cross entropy, and then we generate soft labels using a teacher model, and finally we learn a student model. We are learning this student model by just a cross entropy and labeled and unlabeled tokens. So this stands for labeled data, this stands for unlabeled data, but we can use the cross entropy loss for both of them. And there are entity types and corresponding numbers. If you just write an email and register for this data set, they will give you the data set in 3 days. Of course, there are other data sets as well, but if you like clinical data, biomedical, medical, this one is nice, but the rest of them are in different domains.